Here we go. So here we're talking about translating functions. And this is 2.6.1. And just before we kind of break down what translating means, you know, for this course, if you translate between languages, right? If you translate between languages, you're going to have different words for, say, if you have the word dog. So there's probably quite a few languages spoken in this class. We could think of, 10 ways to say dog, right? But the concept and the meaning of dog doesn't change. Just like with these shapes. When we're translating, we keep the same shape. Say if we had a parabola, we keep the same shape. But translating keeps that identical shape, and it just shifts it up, down, left, and right. Okay. So our root shape that we're going to be dealing with today mainly is this one right here, which we've become acquainted with. It's a parabola. F of x is equal to x squared. Okay. So that's what we're dealing with today. And we know that a more refined definition, it's a shift of the function horizontal, left and right, or vertical, up and down, by a constant k, by some constant. And they're going to kind of work in different ways based on if we're dealing with the x or f of x values. X being the independent, f of x being the dependent. We'll break that down in a moment. Again, it does not change the shape of the function. It just moves the position. It just moves the position around up, down, left, or right. So go ahead and get down to that for a moment. Okay. Our two types. So we have two types of translations. We have, now think about this. Our independent variable is x. You can think about this because x is generally the value, x or t. This is the value, the variable that we are inputting into a function to find our f of x, right? We go in, we substitute or evaluate for x, then we get a different f of x. And that's generally how we're going to approach this. Our independent variable is x. Our dependent variable is f of x, aka y, because we input different values for x, and we get different f of x values. The f of x is dependent on what we input for our x values. Okay, so that's why this is our independent. When we shift using the independent variable, we're shifting horizontally. And that kind of makes sense here because we are manipulating our x value, and the x values are along the horizontal x-axis. Okay, so that's why when we shift here, our independent variable, we get a horizontal shift. And it's denoted by this function, or this notation, f of x plus k. So if you look close here, remember that with function notation, anything that's in the parentheses, right, I evaluate, I substitute it in for my x value over here. So since we're manipulating the independent variable here, what we're doing is taking the independent variable, our x value, and we're just going to say, we're going to add some k value to it, and then plug it in and work that out. On the other side, dependent variables, as far as our f of x goes, this is our vertical shift. And this makes sense too because if we are translating and adding a constant to this f of x value, we're going to shift up and down because f of x is along that y-axis. It is really the value at the y-axis. So when we're doing a dependent variable shift, we're going to have a vertical shift because that's related to y, and y is up and down, x is left and right. And then we're denoted by this f of x plus k. So whatever you got for f of x, after you plugged in your x, you got some f of x value. Now we're just going to add k to it. Those are really nice to work out as far as using tables, because whatever you got for f of x, for your root formula, you just have to, for your root function, you just have to add k to it. And that's your new, we'll call it g of x, because that's our translated function. All right, these shortcuts, I'm going to say slash double check, help us double check if we graphed it correctly. So remember that for for the independent variable and the dependent variable, we have different kinds of shifts. Independent is talking about x, so we add the k value in with x and then work it out. So we're talking about a shift left to right. This isn't quite intuitive, but when k is greater than 1, we shift to the left. When k is less than 1, we shift to the right. Okay. This is just how we're going to double check our stuff at the end. You'll see the shortcut as you start to do these. I think you might use the shortcut in some situations here today. Next we have our dependent variable, y. Let's look at that. Y, which in function notation is just this f of x. Whatever you got for f of x, you would just add k to it. There's a difference. So up here we added k to x and then worked it out. Here we worked it out and then we add k and shifted it up that way. Shifting up and down, this makes sense actually. K is greater than 1, we go up. K is less than 1, we go down. So this is like a lot of different parts of the puzzle. All these notes are kind of parts of the puzzle. I think we have to see a couple examples before this will totally click together. So go ahead and finish jotting down those notes if you are. I'll set up this side. It's going to be right here. Set up this side for the next. I don't know why. It's always funny to me when shit's like that. Oh, nice. That'll work. Great. All right. I think we're good with the shortcuts. Let's actually look at the dependent variable one first. So with the dependent variable, I really like doing the dependent variable first because if we already have our table for f of x is equal to x squared, remember this is just a parabola going right through the origin. It's going right through the origin, and it has the general shape going through the origin, standard parabola, like so. Okay, so this one is f of x is equal to x squared. All right. Now let's see what situation we have. We have the dependent variable, so what we're looking at is after we evaluate values for f of x, all we have to do with the values we get for f of x is add our k value to it. We add k to it. K value is 2. So, sorry, let's rewrite that. So really what we have in our new equation function we're going to have is called g of x, which is just what we had for f of x, x squared, plus our k value, plus 2. So let's look to see what happens with this. I did all these values right here in this table. And let's look at this one first example when I plugged in negative 2. So when you plug in negative 2 to x squared, it's negative 2 squared. We just get 4. Okay. Now, if I go over here, I could do these one at a time, and you might do them one at a time if you want to see how this works, or if you're confused by the shortcut here. But if I have negative 2 for g of x, I plug in negative 2. Right? That's 4 plus 2. Right? Negative 2 squared is 4 plus 2. But here's the situation. This right here, this x squared, we already worked out what all those values equal over on this table. So if I'm looking at this, when I plug in negative 2, what I could say is, well, x squared, let's see what x squared equaled for negative 2. Oh yeah, when I plugged in negative 2 for x squared, I got 4. That's great. So now, if it's just 4 plus 2, that's how I'm going to get 6. Okay. Now, you could even forget about all the shortcuts, all the rules, everything, and just go in here with the table, plot out each point, and then just graph it. You could do that. But if we look to the shortcut, since we know this is looking at a dependent variable, it's looking at the dependent one, the f of x, which changes based on what x I put in. It's just looking at f of x and just adding k. So if I just need to add k, let's see what happened. 4 plus 2, 6. All right. 1 plus 2, 3. 0 plus 2, 2. 1 plus 2, 3. 4 plus 2, 6. You see? So when we have the dependent variable, we can actually just work out this root function. And then since it's just whatever value I got for f of x plus k, it's just whatever I got for f of x plus the k. I find my f of x, I add 2, and that's my new value for this other function over here. You'll see how it connects right now. See how. So let's plot some of these. I say always plot your zeros. In this case, when x is 0, y is 2, so that's my y-intercept right here. Let's see, we have 1 and 3, negative 1 and 3, and then we have 2 and 6. Negative 2 and 6. So once you get enough points here, you can see that's symmetric. What's the line called that breaks up the parabola again, that makes it symmetric on both sides? What do we call that? Line of symmetry. Good. So what we're going to do is we're going to just complete this. And it's the exact same shape. The parabolas are always going to be the same. We're not dealing with what's called a transformation. We're not stretching it or squishing it at all. Here we're just moving up, down, left, right. So x squared is here. Then we have g of x, which is just the x squared plus 2. So what is the difference between those two graphs? What was the difference between the x squared, where it starts at the origin, and the g of x? What happened? What kind of shift did we have? Was it left or right? Up how many? Good. So I would say that this had a brick. This had a shift up by 2. If it was to the right, I'd say it had a shift to the right by 2, left, shift to the left by 2. But basically all this did was it took my f of x value, and we added 2. So what we did was move everything up by 2. Okay. So when we have dependent variables, when you end up with a problem like this, it's going to be pretty quick, because you can have this table of x squared just off to the corner, and then really all you have to do is compare those. What's different? Okay. All right. Dependent variable. And independent variable. Okay. So independent variable, remember, is modifying, shifting my independent variable, which is my f of x, shifting it by 4. Okay. So in this case, oh, I said that backwards, excuse me. Independent variable is x because that's the one we input and it changes our f of x value. So what we're doing with this is shifting whatever x value we were going to plug in, we're just shifting it by whatever k is, in this case 4. So in this case, that plus 4 isn't on the outside. The plus 4 is combined on the inside here with x, because we're really just going to shift that x value first and then work it out. So this one has a little more mental math, but let's see what happened here. This is the same table that I had up before, x squared. Now, to find g of x, really what I'm doing is, whatever value I plugged in for x, say the negative 2, plug in there. Whatever value I plug in for x, I'm going to add 4 to it and then square it. So instead of working it out and then adding our k value, now we add the k value directly to x and then work it out. So let's do it together. Negative 2 plus 4 is negative 2 plus 4. 2 squared, 4. Negative 1 plus 4, 3 squared, 9. 0 plus 4, 4 squared, 16. 1 plus 4, 5 squared, 25. 2 plus 4 is 6 squared, 36. All right. I'm going to put a couple more spaces here to plug in some other numbers. Somebody just looking at the table, tell me why I need to look at some other x values here. Why am I not going to have enough information just from the table supply? Anybody see that? you don't see it, I'm going to start to graph it, and I think that to see what I'm getting at. I'd say use -2, -1, 0, 1, 2 as much as you can, but then let's go and find some other x values if we need it. Yeah, Jason?
-1 and -2 have 4 and 9, which is quite different than 25 and 36 and 1
Good, good. Does this do the point, perfect. And addition to that, do these points show where it hits the x-axis? What value would we need to have for our y value in order to be at the x-axis?
0.
0. Okay. So we haven't figured out where that's going to be yet. Who can look at the equation, though, and say, what value do we need to plug in for x in order to get g of x to be 0? -4. So watch, I'm going to do -4. How about we do -6? Okay. So if you didn't get the logic and math with that, you can just say, I need to just find some more points. After you start to graph it, you'd see that it looks like, let's see, it was going to look like, Okay. It was going to look like 2, 3, 4, here, 5, 6, 7, 8, 9. It's kind of looking way up here is 16. So it's looking like that. It's not a line. I know that it's a parabola, so I'm guessing it's going to go somewhere like this. So if I hadn't graphed these right here, I'd end up with something similar to this, and I know it's not enough. I like that we do -4, because -4 plus 4 is 0 squared is 0. -6 plus 4 is -2 squared is 4. So let's see, we have -4 and -6, we're back up at 4. So now I see that, oh, the parabola looks like that. Now I can graph enough of it. If you just want to think about this as, oh, I'm going to plug in some points, work out my function, that's kind of more the first level. Once you start to think about how to go and make some shortcuts between here and here and what exactly that means. Just happy for this lesson? Yeah. All right, we had x squared right here in green. What happened, what kind of shift did we have to get to our g of x? What kind of shift did we have? How many? So this was a shift left by 4. So for the homework class work, I want to see this, the type of shift. I want to see the graph. And I want to see a table for the new function g of x, whatever that's going to be. Okay? So let's see. Okay, bonus question. Bonus. We are going to look and combine both of these. So watch. What if we have this h of x, this new one that combines x plus 4 plus 2. All we've done is we took this root function, right? We added a value in with the independent variable, and we added one with the dependent variable here. So let's look to see, what do you think this is going to do? If I just had this, if it was just x plus 4 squared, then I'd be dealing with the independent problem I just did, the independent variable. But since, oh, there it is. Oh, just kidding. What are you talking about? There we go. Whoops. All right, so if it was just x plus 4, I know that it would end up being overshifted to -4, and it would look like that. If this was just x squared plus 2, I know that it would be up here at 2, and it would be a graph like so. Sorry. So together, where do you think I'm going to have to place this graph? This is kind of like a little next level. So the blue graph here was if this was just x squared plus 2. The green graph is if this was just x plus 4 squared. So we have those two graphs right here. How about when they're both together? Where's the vertex going to be? Maybe that's the question I can ask. Yes, you know? No. So when I combine these two functions, really what I've done is I've taken g of x, which is x plus 4. I've taken, let's call it k of x, which is x squared plus 2. I've graphed both of them, and if you were to combine them, then we'd end up with the parabola up here. It's kind of the combination of the two. And this would be at -4, 2. All right, that's just kind of like another idea on how to look at a function in different parts. You won't have a question like this today, but I want you to start to think about the translation between those two and how that affects where it is. Okay. So, but for today, you need to graph, you need to show a table and show how it shifts for each problem. And let's see, what should we do today? What should the giveaway be? Anybody have suggestions? A Kit Kat.
Kidneys.
Half a Kit Kat? Whole Kit Kat.
Gift card giveaway.
Oh my, I'm not buying any gift cards. Sorry.
How about
But I have Kit Kats.
How about pens? I need new pens.
Okay. If you're the 79th subscriber, you get a Kit Kat and a pin from the Lost and Found box.
I got this.
Yeah. All right, subscribe on 3. 1, 2, 3.
Subscribe.
Yeah, it's Monday.